Good morning, students. Today we are going to prove the DeMorgan's law by Venn diagram and also algebraically. So, DeMorgan's law we have written already in the previous part 6. That was the number 6 law of the set laws. So, I'll take one of the DeMorgan's law. Say this was there, A union B dashed equals to A dashed intersection B dashed. So this was one of the DeMorgan's law we have seen. So what we will do first, we will draw the Venn diagrams. Okay, so how to draw the Venn diagrams? Nicely in your copy with scale and circles. You can draw freehand circles as well, but in that way you have it needs to be a little good in shape. That's it. So what we do, the LHS part is A union B. So what we will do, we will take A and take B, and this is A and this is B. So what is A union B? A union B is this, the shade. The throughout shade will be A union B. Below you write what you are getting, A union B. Okay. So the next diagram will be, obviously we try to plot A union B whole dashed. That means the part which is outside A union B. So this is our U, actually, the universal set, whole thing. So look at this, the dotted part actually denotes the A union B whole dashed. Okay. So this is the right side, we already got the right side. Now the left side we will try to draw. The left hand side we have drawn, the right hand side we will draw. So the right hand side is the same diagram you try to draw. One thing, while drawing the Venn diagram, always retain the similar kind of shapes of the circles. Say here in my diagram, A is a little bigger than B, so you have to draw like this, that means certainly AB cannot be bigger than A, so that it is a little comparable. That means the diagrams are in pace. Okay, the diagrams are more or less similar. So here what I do, I have drawn A and B. So I will try to draw A dashed. A dashed means everything outside A will be A dashed. Look at it. I am drawing through B also. It's everything outside A, it's A dashed. Okay. So this is A dashed. And I will draw B dashed as well. So if I draw some index over here, this slant shades, it denotes A dashed, and say the standing kind of shades, it denotes B dashed. So I will draw B dashed as well. So B dashed will be some kind of this. Okay. So here what we did, we have seen A dashed, we have seen B dashed. And what is the intersection between them? Of course, the part which contains both the kind of shades, the oblique shades as well as the vertical shades. So mainly what we see, this kind of shades as well as this kind of shades is actually the area of intersection. So if we draw it more freshly, we will get something like this. If this is A, this is B, we will get something like this. Please look at it, try to understand. So this will be like this, and the vertical shades as well. So this becomes, these two diagrams are same. So therefore we can write that LHS is equal to RHS. So by Venn diagram we have proved the DeMorgan's law. So now what we are going to do, we are going to prove the same law algebraically. So I will erase this part. You can pause the video and look at it. Always I instruct that go through the previous parts. Those are actually needed for understanding this. And here you understood, right? These are A and B, and this is the part outside A and B, which is A union B whole dashed, and here you got the same thing, A dash intersection B dash. So see, both the diagrams are same. So the law is justified, it's proved. Okay, let us do the same thing by algebraic approach. So what we do, let X belongs to A union B whole dashed. So if X belongs to A union B whole dashed, that means that X does not belong to A union B. Obviously it's outside A union B whole dashed. That means it does not belong to A union B. So here a strange thing we observe, that we write X does not belongs to A and X does not belongs to B, and both the statements are correct. Generally what happens, union we replace with OR. But here, since both the statements are correct, this and this both are correct, because the X element is neither in A nor in B, so we have to write AND over here. Okay, so we have to write AND over here. This union we replace by AND. So after that, if X does not belong to A, so X will belong to A dash, and X belongs to B dash. So removing the AND and converting it to intersection, we can combine this and write, therefore that means it implies that X belongs to A dash intersection B dash. So we started from here, ended over here. Okay, but you always know that this is half of the sum. We have only proved that LHS is a subset of RHS. That means we always know that if X belongs to A implies that also X belongs to B. A is a subset of B. It's not A equal to B. Okay, so if the opposite is also true, Y belongs to A is a subset of implies that Y belongs to A also. So Y belongs to B implies that Y belongs to A also. It means it implies that B is a subset of A. And with the help of both of this, we can easily say that A equals to B. So this is the logic which we use for proving every set laws. So here what we write, so we have started from here that X belongs to A union B whole dash, and we ended over here. So we can write over here that A union B whole dash is a subset of A dash intersection B dash. Look at it. We have done till here. Till here we have done. Now the other half we need to do. Otherwise the sum will be not completed. So let us do the other half by taking Y as well. Let Y belongs to this part. That means A dash intersection B dash. That means obviously what we write, Y belongs to A dash and y belongs to b dashed. Okay. So next, y belongs to a dashed means what? Y does not belongs to a and y does not belongs to b, and they are also connected by and. Let's actually see, the steps are same. We are writing them in a reverse order. If you start from here, you see that it's a reverse order. The steps are moving out. But while writing, you first understand. Okay. For exam purpose, you can easily, this is a tip to you, you can easily follow the reverse purpose. But for understanding this, you can always understand this, how it is happening. So that means here y does not belong to a and y does not belong to b. We are in this step. That means y does not belong to a union b. Look, here and is again converted to union. So this naturally, this generally does not happen. And is converted to intersection. But here this is a special kind of thing where we are denoting the complement. So this is happening over here. The last step will be, therefore y belongs to what? A union b whole dashed. Okay. And it means that y belongs to a union b whole dashed. That means we have reached the left hand side. Therefore this is a subset of this. So we can write a dashed intersection b dashed is a subset of a union b whole dashed. So the a dashed intersection b dashed is a subset of a union b whole dashed. So we got both the part. This is say part 1 and this is say part 2. So part 1 and part 2 both are done. So we can say that from 1 and 2 LHS is equal to RHS. That means this part when both are subset of each other, A is a subset of B and B is also a subset of A. So we get A equals to B. Here also the right hand side is a subset of left hand side, as well the left hand side is a subset of right hand side. So we get both the parts to be equal. Thank you. We will proceed in the next video, part 8. Okay.